In this example, a 5 kilogram particle is attached to a 1 kilogram particle by a light inextensible string. We have a right-angled wedge of mass 8 kilograms. As soon as the system is released from rest, the 5 kilogram particle flies out and maintains a constant angle theta from this surface. The wedge rests on a perfectly smooth horizontal surface. Let's start with the forces on the 5 kilogram particle. Well, of course we have its weight mg. We also have a force on it due to the string. Let's say the magnitude is t. As you can see, unlike previous examples, we don't have any force on the 5 kilogram mass due to its being in contact with the wedge. Let's consider the acceleration of this particle. We are assuming that the 8 kilogram wedge moves to the right, and when we do the calculations, A will indeed come out to be positive if we take directions to the right as positive for this, so indeed that's what happens. But we might also expect the 5 kilogram mass to move downwards. It's got greater mass than this particle here, of course, so it's going to move down, but it's also going to move to the right. You know, we are assuming that theta is fixed, so sometime later the wedge might be here. Okay, it's moving to the right, but our particle now, this angle is still theta. It hasn't changed. That's what we assume is going to happen. But the 5 kilogram particle has moved down, and of course the 1 kilogram particle has moved further up the wedge. So the acceleration vector will look something like this. Well, it's going to be in the same direction as the resultant force. If we complete a parallelogram here, this is our resultant force, so the acceleration vector by Newton's second law is in that same direction. We just multiply 5 by the acceleration vector to get the resultant force vector shown here in red. Now, to make the diagram easier to read, I'll just exaggerate a bit. So I want to show a component of this acceleration along this direction here, the string, and a component that's perpendicular to this imaginary surface. So let's set up our xy axis. Let's call the acceleration of the 5 kilogram particle b. Its components in the y and x directions are positive, as you can see. So we choose the positive x direction as down this imaginary surface, and the positive y direction as perpendicular and into this imaginary surface. Let's look at the resultant force on the particle in the y direction. So that's F sub y. T has no component in the y direction. Only the weight 5g has a component. So our angle in here is theta, the same as this angle. We don't know what theta is. We do know that it's fixed. But if we multiply 5g by sine theta, we get this component here shown in green. And by Newton's second law, that's the mass, which is 5, times the y component of the acceleration. We can relate this y component to the y component of the acceleration of the wedge, since this imaginary since the particle is always in contact with this imaginary surface as the wedge accelerates to the right. So we resolve the acceleration of the wedge in the y direction, so that's this direction here. It's the direction of the y-axis, perpendicular to our imaginary surface. So A is the magnitude of the wedge's acceleration, so we need an angle. And okay, so this is the component that we're after. We want this to be parallel to our y-axis. This component here, the x component of A, is parallel to the surface, this imaginary surface. The imaginary surface makes an angle 90 minus theta with the horizontal, because we have a right angle here. Both of these angles add up to 90. So this angle here must be 90 minus theta, which means that the angle over here is theta, because these two angles add up to 90. Alright, so now we can see that this component that we're after is A cos theta. So that's the y component of A, and that's equal to the y component of B. So now divide both sides by 5 and we can get the acceleration of the wedge in terms of theta. Let's look at the x component. So we need the x component of the weight, this vector here. Well, that's just 5g cos theta. That's in the positive x direction. T is in the negative x direction. By Newton's second law, we multiply the mass by the x component of the acceleration. Now let's look at a 1 kilogram particle. Well, let's get an idea of where it's going to be sometime after the wedge has moved. Okay, so we know the wedge is going to move to the right. Well, that's what we're assuming, and that actually is what happens. The particle is going to move up the incline, as we saw before, because the more massive 5 kilogram particle is going to move down. So the acceleration of the 1 kilogram particle will look like this here. Again, we will resolve the acceleration in a direction parallel and perpendicular to this surface. So here's the component parallel and here's the component perpendicular. We want both of these components to be positive to make life easier, so we want to take up this incline as positive and perpendicular and away from the incline as positive. Let's call the acceleration c, and we have its two components, c sub x and c sub y. Here are the three forces acting on it, so let's call the force on the particle due to the wedge R. Its weight is 1g, and with string tension T, same as this here. Let's look at the forces on the particle in the y direction. So to do that, we need to know the angle of the wedge. Let's suppose that the angle A of this incline is such that tan of A is 4/3. If tan of A is 4/3, we can write down what cos A and sin A are. So we resolve the weight vector in the x and y directions. The angle in here is A, as we've seen before, same as this angle. So side adjacent to A is g cos A, where cos A is 3/5, so this component is 3/5 g. And this other component here is g sin A, so that's 4/5 g. So now R is in the positive y direction, and 3/5 g is in the negative y direction. So those are the y components. T has no y component. By Newton's second law, that's the mass, which is 1, times the y component of the acceleration, which we would call c sub y. Okay, c is the acceleration. Here is its y component, c sub y. Now, just like we've seen before, we can relate c sub y to the y component of the acceleration of the wedge. That's a sub y. So we resolved a in a direction perpendicular to this. That's the y direction. Okay, so here's our angle A. So we multiply A by sin A, where sin of A is 4/5. So I've replaced c sub y with 4/5 A. What about the x component? Let's do that. Well, we have t pointing in the positive x direction, and we've minus 4/5 g, so t minus 4/5 g. We apply Newton's second law, and we take the mass, which is 1, by the x component of the acceleration, c sub x. Now what we can do is we can relate the x components of the accelerations of both particles. Now we've seen this before. Of course the x-axes are different, but we're dealing with the actual accelerations here, of course. We're applying Newton's second law, so b sub x is an actual acceleration, and c sub x is also the actual acceleration. So c sub x is in here, of course, this vector here. And they're the same. C sub x equals b sub x. So we've seen that before, where two particles are attached. They're connected by this inextensible string. So the acceleration in this direction for the 1 kilogram mass is the same as the acceleration in this direction here, because they're accelerating around anti-clockwise. As you can see, they're connected by the string. So we might as well just write b sub x in here to get rid of that unknown. Okay, I'll drop these references to the x and y components just to avoid confusion, because we're dealing with two different axes here. Now let's look at the forces on the wedge. With these two tension forces, at the top we have a force R on the wedge due to the 1 kilogram particle, okay, equal and opposite to this R here, of course. We have the weight of the wedge, HE, vertically down, and we have a force on the wedge due to the surface, N. Of course, all the vertical components have to cancel out, so we are only interested in the horizontal components. They're the ones that make up the resultant force. So let's get the horizontal component of this force here. Well, here we have angle A, same as this angle. So the side adjacent to A is T cos A. Over here, you know, here we have theta, which is fixed. We don't know what it is, but in this angle in here is also theta. So we want the side opposite theta. So that's T cos, T sine theta. What about the horizontal component of R? Well, we've seen this kind of thing before. We know that this angle in here is the same as this angle down here. So we want the side opposite A. So this is going to be R sine A. Sine A is 4/5, so we get 4/5 R. Now, the acceleration is to the right, so that's the direction of the resultant force. So the resultant force comes from all these horizontal components. So we have T cos A to the right, minus T sine theta to the left, and we have minus 4/5 R. That's pointing to the left. By Newton's second law, that's the mass of the wedge, which is 8 times its acceleration A. Cos A here is 3/5. Now at last we have 5 equations, and we have 5 unknowns. The 5 unknowns are A, theta, B sub x, R, and T. Now remember, B sub x was the component of the acceleration of the 5 kilogram particle parallel to this imaginary surface. It's also the acceleration of the 1 kilogram mass parallel to this surface of the wedge. Let's refer to this component as P. So here is P. Okay, they're meant to be the same, of course, in magnitude. I just prefer to write P than B sub x. Okay, so one approach to dealing with these equations is to start by getting rid of terms involving theta, like tan of theta, cos of theta, and sine of theta. Well, if we take the first equation, we see that tan of theta is A over G. So if we make this construction here, angle theta, make the side opposite theta A, side adjacent G, well, you can see that the hypotenuse is going to be root A squared plus G squared. So we can write down sine and tan of theta in terms of A. So we could pop these in for cos and sine. Now these 4 equations are very complicated to solve by hand, so I used an online program to solve them. And these are the values I got for A, R, P, and T. Now once we know what A is, well, we can use tan theta equals A over G to solve for theta. So we found the acceleration of the wedge. It came out to be positive, so indeed the wedge is moving in the positive direction, which is to the right. That was the positive direction for the wedge. P came out to be positive as well, so just as we expected, the 5 kilogram mass is moving in its positive direction, which is down this way. Now let's look at the acceleration of the 5 kilogram mass relative to this pulley. Well, we get the component of the acceleration of the wedge, in the direction of the 5 kilogram mass. That's parallel to this vector here. So we have to project the tip of A onto this line here. We have a pair of vertically opposite angles here. So this angle in here is theta, same as this angle here. Okay, so there's our opposite angles. So I'm showing the same picture over here. I've just exaggerated the size of A to make it easier to read. So here's our angle theta. So it means that the one next to it must be 90 minus theta, because this dotted line is vertical. If this angle is 90 minus theta, this one over here is theta, because we're in a right angle triangle. So what we're looking for, this component here, parallel to vector P, is the hypotenuse A times sine of theta. So we plug in the value for A, this value here, and the value that we got for theta that we saw previously, and we get this value. So without using a relative acceleration formula, we know what's going on intuitively. So the pulley has an acceleration in this direction, but you can see that it's in a direction that's opposite to P. So in a sense, the pulley and the 5 kilogram mass are both moving away from each other. Okay, so we would effectively add these two accelerations. So the answer is going to be greater than 7.17912, because the pulley in a sense is moving away from the 5 kilogram mass. It's not stationary. If the pulley was stationary, if the wedge was stationary, well, this would be the acceleration of the 5 kilogram mass. Since the wedge is not stationary, it has a component parallel to P and pointing in a direction opposite to P, we effectively add the magnitudes of these two vectors. So if you do that, you find the acceleration of the 5 kilogram mass relative to the pulley is 7.215 meters per second squared. So that's how much it accelerates away from this pulley. Now let's consider the acceleration of the 1 kilogram mass relative to this pulley. So I'm showing the acceleration of the pulley down here. It's to the right, of course. We're interested in its component parallel to this vector. Well, this vector P, or parallel to the incline. So we're given this angle in the problem, and it's the same as this angle here. These are a pair of Z angles. So in this right angle triangle, we want to multiply A by cos A. We have tan A, so cos A is 3/5. We have A, so here's the component, 0.355644. So in a sense, the pulley is moving, has a component pointing towards the 1 kilogram mass. So both the pulley and the 1 kilogram mass are closing on each other. So that means that we add these accelerations. We end up in an answer that's greater than the actual acceleration of the 1 kilogram particle.